Okay, so two things. First of all, this will be the third time I try to record the third video because my microphone keeps dying. Evidently the batteries must be going, so it won't hold a charge for very long, which is good for you. It means I won't talk as long. The second thing though is I noticed that at the end of this last video that you just finished watching, my energy level kinda dropped to something like this. Sorry about that. Particularly here at the end, I was talking about how electrons are delivered through the wire down an electrode, and I'm supposed to be talking with some sort of enthusiasm about platinum and gold electrodes and how they can be used to deliver electrons into the solution without having to worry about any sort of interaction or reaction. But instead, I think I said it like this, and it was just, sorry about that. So let's get some enthusiasm. This shouldn't be shocking to you since we're learning about electricity. That pun didn't work there at all. Sorry. All right. Let's move on to the next topic. The next topic is about potential energy versus and the Gibbs free energy law again. This is one of the equations we have in the equation sheet. Delta G prime is equal to negative NF E cell. This is our same delta G from earlier in the year. Our free energy, Gibbs free energy equation earlier in the year was delta G equals delta H minus T delta S. Remember those days? They were about a month and a half or so ago. And we need the delta G could tell us whether or not a reaction was spontaneous. Listen to the enthusiasm. Spontaneous or not. And in order for a reaction to be spontaneous, delta G needed to be what sign? That is correct. It needed to be negative. If you have a negative delta G value, then the reaction could occur spontaneously. And in the previous chapter with thermodynamics, we were comparing the enthalpy and the entropy and the temperature values to calculate whether or not a reaction would be spontaneous. Well, here we have a new delta G equation, and this is the same delta G. It's just based off electricity and whether or not the electrons will flow in the directions we expect them to. If we calculated delta G as negative, then the electrons will flow based off of how the reaction is written. If we have a delta G that is positive, then the electrons would not flow the way it's written, but it might flow in the reverse direction. More on that in a second. So what does the N, the F, and the E stand for? The N is the moles from your balanced equation. So you just look at your equation and figure out how many moles of electrons are being exchanged. Say silver is losing 1, but aluminum is gaining 3. Well, you have to balance the reaction. Silver has to lose 3 if aluminum is going to gain 3. And therefore N would be equal to 3 because each element is gaining or losing 3. So we're just going to look at the reaction to figure out the number of moles. Faraday, this is Michael Faraday. He's a very famous scientist who did a bunch of very interesting physics work. I suggest you look him up. He's got some great ideas out there. One of the things he was working on was figuring out charges and the values of charges, and he settles on what the charge value is for electrons and things like that, and he's working on those values. And so he's given credit for this constant, 96,485. The last value is accidentally wrong. Let's change the last value to a 5. So that's the number of coulombs, which is a measure of charge, that a mole of electrons delivers. So if you have a mole of electrons travel by, this is how charged up you get, 96,000 coulombs worth of charge. And then our last one, the E, this is our voltage. This is the cell's voltage. We just finished talking about how to figure out voltage, flipping around equations and things. And we had said that we wanted voltages to be negative for a cell to flow properly. No, that's not true. We said that we wanted a voltage to be positive. A positive voltage means that the electrons are going to flow from the weaker element to the stronger element. If it's negative, that means that the voltage is set up wrong. The battery's not going to work the way we want it to. So let's do an example of that, situation where it's not going to work the way we want it to. Here we have zinc ions attempting to steal electrons from copper to make zinc atoms and copper ions. If we go to a redox table and look up the voltages, we would see that zinc in this reaction is negative 0.76, the way it's written. To have zinc ions become zinc atoms is negative 0.76. And to have copper become copper ions is negative 0.340. The problem with that is the way this reaction is written, the cell potential right here would be negative 1.10 volts, which is a problem. The way this reaction is written, the electrons wouldn't move as we want them to. Zinc is not strong enough to take electrons from copper, so this reaction wouldn't really happen. But let's also show that with the Gibbs free energy equation. So here's the Gibbs free energy equation. Delta G is equal to negative N F E. N is the number of moles. How do I figure out it was 2? Well, zinc was a positive 2 charge, and then it gained 2 electrons. Copper was a 0 charge, and it lost 2 electrons. That means there are 2 electrons exchanging between atoms and ions here. So N is equal to 2. F is Faraday's constant. Please do not memorize Faraday's constant. This value is given on the equation sheet and can be found on the equation sheet. Just look it up, 96,485. Can't fix that 6 to a 5 there, sorry. Coulombs per mole of electron. And then the voltage we just calculated was negative 1.10 volts. Volts are the same as joules per coulomb. We multiply these things together, and we have 2 moles of electrons. It cancels out moles. We have coulombs. It cancels out coulombs, and we get joules. So the delta G value for this reaction is a positive 212 kilojoules. So this reaction would not be spontaneous. So under standard conditions, this reaction should not occur because zinc ions are not strong enough to steal electrons from the copper atoms. Therefore, we would not have the reaction occur as written. The reverse reaction might occur, but not the forward reaction. Because if we had the reverse reaction set up, the voltage would be positive, and then delta G would be negative, and yay! So it is possible to do the reverse reaction. There is your delta G equals negative NFE. Here is an example. Let's actually try to figure out the actual E and delta G for a reaction involving these 2 potential equations. We have vanadium oxide, and we have zinc. We have to figure out which of these reactions has to be flipped around. One of them must be. They both have electrons on the reactant side, and that's a no-go. So we have to flip one of them. Also, we have to multiply this reaction by 2 so that the number of electrons are equal, because that only has 1 electron where the zinc has 2 electrons. So which one should we flip? Well, let's look at the 2 voltages here. The first voltage is a positive 1.0. The second voltage is a negative 0.76. If I flip the second one, I would have the 1.00 and a positive 0.76 for a combined voltage of 1.76. So I need to reverse or flip the second reaction around for this reaction to work properly. So the total reaction would be 2 vanadium oxides, 4 hydrogen ions, and the zinc solid is now a reactant, producing 2 vanadium dioxides, As I was saying that, I just realized that this VO2 and this VO2 is the same. There's actually a 2 in the wrong spot in the notes. This 2, I'll change color so everyone knows where it's supposed to be. This 2 is supposed to be here. It's supposed to be a positive 2. That's VO plus 2. So that there is a change occurring. Alright, what else do we have here? 2 waters. There was 1 water. We multiplied everything by 2. And I still need the zinc ion. So that is our total reaction. When we add everything back together, we have the 2 vanadiums, the 4 hydrogens, the 2 vanadium oxides. That's how our electrons are being gained right there by the vanadium, waters, and the zinc. We could go back into here if we really wanted to and kind of rip this apart. This is a +1. It's -2, so the vanadium is a +5 right now. But over here, the vanadium is a +4. Sorry, +4. Right, it's +4. So we have one, the charge is different. The oxidation state of the vanadium is different by 1 because it's gaining 1 electron. Good. So here we go. We have 2 electrons. Faraday's constant, the voltage. So delta G for this reaction is negative 340 kilojoules. What else could we do with this one? Which element is at the cathode? Which element is at the anode? Which one is gaining electrons? This one is. So this is the cathode. And after we flip the zinc around, the zinc would be the anode because it's losing electrons once we flip that reaction around. Good. Okay, our next scenario is kind of weird. Let's zoom in for a second and explain it with these 2 pictures. We're going to start first with this picture, and just this is going to be very obvious, I think. We have a 0.5 molar nickel solution, and then we have a piece of nickel stuck into it, solid piece of nickel. We have a 0.5 molar nickel solution and a piece of nickel stuck into it. Which side is going to pull better on the electrons? The nickel in the nickel solution or the nickel in the nickel solution? Well, neither. They're identical solutions, right? They're identical solutions with identical piece of metals, and the 2 sides are at equilibrium, so there shouldn't be a shift one way or the other that we would notice because they're at equilibrium, so there'd be no shift. The inverse of that is true. If we had tainted these solutions one way or the other, they wouldn't be at equilibrium, and a shift would be required. So let's look at this picture here. We have a very concentrated nickel solution. This is a 1 molar nickel solution here versus a very dilute nickel solution. This is 10 to the -3rd, which means there's very little nickel in this side. On the left side, the concentration is very low. Here the concentration is very high. So these are not at equilibrium at all. Well, how are we going to get them towards equilibrium? We need this concentration to increase, and we need this concentration to decrease. The only way for this side to increase would be if nickel atoms went into the solution and came out of the metal. On the other side, maybe we have nickel atoms coming out of the solution and attaching themselves to the metal and becoming pieces of the metal and plating out on this metal. And that's what we could do. We could actually just create create a current by having 2 different concentrations. So this side, the left side, I should say, the left side, the nickel atoms are going to go into solution, become nickel ions. And if they're going from nickel solid to nickel ions, they have to be losing electrons. And those electrons are going to go through the wire over here And then on the other side, you're going to have nickel ions that were in this solution. Remember, it's really concentrated nickel ions, and they're going to become nickel solid because they are going to gain the electrons that come through the cathode there, through that nickel, and you're going to slowly see the molarity decrease on this side and the molarity increase on the left side as the electrons flow through the wire. So we can actually set up a battery using the two identical metals just by changing the concentration. Now, if you look at the voltage though on this voltmeter up here, it's 0.0888 volts. That is not very many volts. And what's going to happen as these electrons flow? As the electrons flow, the concentrations are going to get closer and closer and closer to equilibrium, and this voltage is going to drop more and more and more. And it's going to slowly go from 0.08, and it's going to drop and get closer and closer and closer and closer to 0. You know, once it reaches equilibrium, right? It's just going to slowly drop until that voltage reaches 0, and at 0 we've reached equilibrium. The two things are equivalent again. Well, so we're not going to do any calculations with anything like this, but we can use it for some of our justification, and we can use good old Le Chatelier's principles to justify some changes in voltage. The electrons will shift from one side to the other side just because of the differences in concentrations. And I've got a little scenario here. What if you had 0.2 molar copper versus 0.05 molar copper? How would the components switch? The 0.05 would gain copper atom ions. 0.25 would lose copper. So this side, the 0.05, where they're gaining ions, they're losing electrons. This would be the anode side. The 0.05 would be the anode side, and this one here, the 0.20, would be the cathode side, because they would be gaining electrons and turning into solid. And I go through and I kind of explain that here. But we're not going to do concentration-based cells. We are going to talk about the impact of concentration differences on regular voltages. So let's keep in mind though, normally we work at standard conditions. We work with a 1.0 molar solution for both the cathode and the anode cell. If we change those molarities, we then should probably compensate for it. And there's a math equation called the Nernst, it's right here, the Nernst equation, that does compensate for changes in molarity. We will not be using this equation ever. We will be just thinking about Le Chatelier's concepts and how it would impact the voltage. But this equation also backs up that logic. So anyway, let's explain how what we're going to do. Let's go down and look at this reaction, this sample question number 1. Let's calculate the E cell for cadmium lead interaction. There's the voltages. Which one should we flip? We should probably flip this one, because then we'd have a positive voltage, and we'd have positive 0.40 and negative 0.13. So the total voltage would be 0.27 volts. That would be 0.27 volts if both molarities were 1 molar. So here is our reaction once we combine them together, and we're expecting the voltage to be 0.27 volts. What I would do is I will throw you through a couple of different possible scenarios. What if the lead molarity was increased? What if the lead molarity was decreased? What if the cadmium concentration was increased? What if the cadmium concentration was decreased? Now it's only going to be the ions because those have to be in solution. The other ones wouldn't have an impact on Le Chatelier's principle because, as we discussed earlier in the year, reaction rates are only dependent on the species which move and have first or second order values, and solids have 0 orders in reaction rates, so they don't actually impact the speeds of reactions. So let's talk about what would happen if we increase the lead. So if I have more lead ions, which way would this reaction be more likely to shift? Did I hear right? I think I heard right from everyone except for Arthur. Should shift to the right to come back to equilibrium. Well, by adding lead, we're not only increasing the potential for the shift, we're also increasing the voltage. Not a lot, just a tiny bit. And that's what, let me just erase that giant blue spiral I made. That's what the Nernst equation is calculating right here. They have more lead than cadmium, plugged them in, did all the math, and look, the voltage went from 0.27 up to 0.299 because there's more lead than there is cadmium. We're not going to do these equations though, so don't worry about that math. Worry about the logic. If I increase a reactant, shifting should try to push it more towards the product side. This means that it's going to increase the voltage. If I decrease the reactant, I should be decreasing the voltage. Increase a reactant, increase the voltage. Decrease the reactant, decrease the voltage. The opposite is true for the other side. What if I increase a product? That would cause a decrease in voltage. And if I decrease the product, it would increase the voltage. And it really becomes all about like equilibrium constants, about products versus reactants. When you increase the product, you're probably getting closer to the equilibrium constant, and it needs to shift back. Or if you're increasing the reactant, you're probably farther away from the equilibrium constant. And we are not going to calculate, again, what the actual mathematical impact would be to the voltage, but how would it? Usually, the molarities are 1, and so what do you plug in here? You plug products over reactants. 1 over 1, log of 1 is 0. 0 times this doesn't matter, so the cell voltage is just equal to the regular cell voltage because we use 1 over 1 for our standard molarities. If they mess with the molarities at all, though, we would use that equation. In the real world, in our world, we'll be fine without it. We'll be fine without it. So you need to look through your book and read about batteries, and also read about corrosion. There's a number of definitions and terms in there about the chemistry behind them. I'm not going to go too much into them. Batteries are just basically stored chemical potential energy, where we've gotten 2 elements separated, and we're kind of using their pull. One thing that's we need to be careful about with batteries is storing them in a stacked fashion is a bad idea. If you store a standard AA or AAA battery, both of those are 1.5 volts, and when stored on top of each other, like in this picture here, the voltages add up, and so 2 1.5 volt batteries become a 3 volt battery, which is usually why you open your remote control and you have a whole bunch of batteries in there. They're trying to increase the voltage, or depending on how they're put into the battery, into the piece of equipment, they might be increasing the voltage, and they might be increasing current. It could be a number of things they're trying to do there. Car batteries are actually pretty interesting design. They have a number of plates. Some are made of lead, and others are made of lead oxide. Let me zoom in there. I'm pretty sure you can't see what the heck I just circled. So you have some lead plates and some, well, this looks good. Let's zoom back out for a second. Sorry about this, guys. You know what? Just get rid of that. Alright. So we have some of these are lead plates and others are lead oxide. So you have lead plates and you have lead oxide plates, and they're submerged in sulfuric acid. Oh, it says right there which one's which. This one's the lead oxide, this one's the lead. They're submerged in sulfuric acid, and so both reactions start the same. Lead plus the hydrogen sulfate, lead oxide plus the hydrogen sulfate. The lead sulfate is made. Lead sulfate is made. So both of them react and make lead sulfate, but the difference is the first reaction gives 2 electrons, the second reaction takes 2 electrons, and they're essentially using the sulfuric acid as the salt bridge. And the electrons leave out the anode and cathode up at the top, and so the electrons, leave out the anode, run through your spark plugs or whatever, and come back in the cathode. And as the electrons come back in, the lead oxide is taking those electrons that the lead just released, but it only does this for a second or two in the very initial beginnings when you start your car. Once the car is actually running, a couple minutes in, your alternator kicks in, and your alternator actually reverses everything. The alternator is powered by the engine, and the alternator causes a voltage that is greater than the battery's voltage and allows the recharging of the battery. And so this reaction, the overall reaction, slowly gets pushed back once the alternator's turned on. And we could have a real series of problems if the alternator is not properly calibrated. The lead sulfate pushes back into lead and lead oxide, and then these plates become refilled. Well, if you run out of lead sulfate completely, but the alternator is still charging it, it's going to continue to try to force electrons into this solution. And down in this sulfuric acid is lots of water, and the water will get broken apart into hydrogen gas and into oxygen gas, and you can get a buildup of hydrogen and oxygen gas inside the battery, and it can explode and pop. It's probably not a very good idea to have flammable hydrogen gas under the hood of a car, but it is known sometimes to have batteries leak gas. And I don't mean gasoline, I mean gas, H2 and O2, out of them from overcharging. Modern alternators, though, kick off and on so that you don't get that overcharging issue. I just went way too far into car batteries. Sorry, I just find them kind of interesting. They represent everything we saw in the little standard goofy battery. Man, this is a quick haphazard picture. There's the salt bridge, except we have lead oxide, and here all of this is that sulfuric acid solution, which is pretty cool, that all of that is the sulfuric acid solution, and so it hits both sides. Corrosion, yes, you need to investigate the properties of corrosion and how iron rusts. It's kind of like a redox reaction, because the oxygen ends up dissolving into the water and grabbing onto the iron and turning it into rust. We usually avoid corrosion on our cars by coating everything in wax, and that waxy seal or a thin plastic seal means that the oxygen never gets to the iron and the water never gets to the iron, and it's all protected. So read through the section on corrosion. The last section, and then we're done. Hopefully This thing is actually still recording audio and not cutting out on me again. Last time it was about here I was recording that suddenly the audio just cut out. It was just really what I wanted to hear when I went to listen to it the second time. So electrolysis. A second ago we were talking about how you could stack batteries on top of each other. So if I put a 1.5 volt battery on top of another 1.5 volt battery, I would get a combined voltage of 3 volts. And let's say this is the negative side, this is the positive side, this is the negative side, this is the positive side. What would happen if I took a third battery, let's just make this one blue, and we put it in here, but instead we put the positive side here and the negative side there, and then we connected it all with a wire. If this was 1.5 volts, but since it's put in backwards, it's like it's negative 1.5 volts. So now the total still becomes 1.5 volts. The electrons are still going to leave the negative. The dominating negative direction would be this direction. And then they'd go through here and they would put energy into this, and the voltage would slowly increase as these two slowly decreased, and this third battery would be recharged by the other two batteries. This is essentially what happens, and this is, by the way, this is such a crude, not true, this is not how you would do it. Don't do this at home. It doesn't work. But this is the idea behind most of our rechargeable batteries, not the actual practice. The practice is much more complicated. This is the general idea, is that you apply a larger voltage, we had 3 volts, against a smaller voltage, negative 1.5 volts, and therefore the larger voltage beats out the smaller voltage and the electrons flow. Since they're flowing in reverse, it recharges it. This act of forcing electrons to go backwards is called electrolysis. Electrolysis is the process of forcing a current through a cell to produce a chemical change. So here we have a reaction between iodine and copper. Iodine is supposed to be a strong nonmetal that takes electrons. Copper is supposed to be a metal that loses electrons. But the way this is written, the iodine is losing electrons to the copper, so it's written in reverse. And if we look at the voltages from a redox table, we see that iodine losing 2 electrons is negative 0.53, copper gaining 2 electrons is positive 0.34, so therefore the voltage for this reaction would be negative 0.19. If we wanted this reaction to run, we should apply an external voltage that's at least greater than positive 0.19. So if I applied positive 0.20, then the combined voltage from my external battery in this reaction would be positive 0.01 volts, and the external battery would force this reaction to go in reverse. This is of course assuming that you attach all the wires and the leads and everything correctly and you put the battery in there the right way. If you put the battery in there the wrong way, no, not going to work. But if you put the battery in there the right way, it should work. And I think a lot of people have accidentally put batteries in backwards. This is the essence of electrolysis, just forcing a reaction to go backwards by applying an even stronger external voltage. Yeah, that's it. Pretty cool. Actually, let me pause for a second. Alright, I had too much stuff showing, and I want to go through this and explain it, not just have you copy stuff down. So we're at the very end, and this is one of the last equations we'll learn for the year. I equal Q over T. That does not stand for I quit. I over QT. Q is the charge, T is time, finally. I is current, how much electron is flowing. Current, electrons flow. The units for current, people usually say amps. Amps is the amount of charge flowing in a second. And a lot of these problems are worked out using dimensional analysis. So if amps are coulombs per second and Faradays are 96,485 coulombs per mole, so I got coulombs and coulombs, I would need time, and then I have all these units. Remember, you can always invert a ratio. Faradays is 96,000 over 1 mole. You could also write it 1 mole over 96,000. And amps is coulombs per second, but you could always write it 1 second per so many coulombs. You can write them inverted. So let's try number 15 and think about what we've been given. How many grams of copper? All right, looking for a mass of copper. Can be reduced by applying 3 amps. 3 amps is really 3 coulombs for every 1 second. Okay? A current is applied for 16.2 minutes. Containing copper positive 2 ions versus copper. That means the copper is losing 2 electrons as it goes from copper to copper 2. Or reverse that. I think we're actually reversing it. Yep, we're reversing it. So the copper ions are gaining 2 electrons through this electrolysis. So what do we start with? Now, I'm going to pull stuff out here at the corner. You probably want to write this down on the left side and just slowly build your dimensional analysis train. We're going to start with time. 16.2 minutes. Why are we starting with time? Because this is coulombs per second, and we need seconds in order to use coulombs per second. So I'm going to convert my 16 minutes to seconds. 16 minutes, I know 1 minute is 60 seconds. There's the conversion from minutes to seconds. Second conversion is going to use the amperage. 3 coulombs per second. There's my amperage being used right now. So I've converted minutes to seconds, seconds to coulombs. If I stopped right now, I would know how much charge had been released after 16 minutes. Charge, coulombs. I can convert coulombs to electrons using Faraday's constant. There we go. There's 1 mole of electrons for every 96,485 coulombs. So I've gotten the moles of electrons. How many electrons are involved in this reaction? 2. There are 2 electrons for every copper. 2 electrons for every copper, based off of what we were discussing right here, that the copper ion can take 2 electrons to come back to copper. And now that I've got the copper, I can go to grams using ye old periodic table. 1 mole of copper should have a mass of 63.55 grams of copper. This might be our longest dimensional analysis problem of the year. Oh, the injustice of it all. So let's just throw the line in there. People write stuff down. There we go. 16 minutes, 60 seconds, 3 coulombs per second, 1 mole of electrons, 96,000. 1 mole of copper is 2 mole of electrons, change into mass. So now I know the mass of copper that can be reduced, meaning the mass of copper that can be produced from copper ions. And this is quite often how the mining industry actually separates out copper ions or gold from slurry. You'll pick up a bunch of rocks in a mine, you grind them up, you pulverize them, and then you dissolve all of the pulverized rock into different acidic solutions. And if you apply a voltage to those acidic solutions, different elements will precipitate out into solids, and then you can gather up the solids as they precipitate out. And here's one last example of the same idea. They're applying 4 amps. That's 4 coulombs per second for 12 minutes. You're converting minutes to seconds, seconds to coulombs, coulombs to moles using Faraday's constant. For every 1 mole of electrons, there would be 2 hydrogen atoms. And then for every 1 mole of hydrogen, 22.4 liters of gas would be produced. So we can calculate the volume of gas produced through electrolyzing water. That sounds like an interesting demonstration to do in class sometime. All right. Briefly interrupted there. So that kind of covers all the things from the notes. Make sure you understand how basic batteries work. These are basic galvanic batteries, how the electrons are flowing. Who's the anode? Who's the cathode? Which way are the electrons moving? Which way are the ions moving in the salt bridge? That's one thing I don't know that I quite hit on. When the electrons are going one direction, the anion, the negative ion, must be going through the salt bridge to keep the loop. All right, that's the loop in this particular battery. If the negative is going to the right, then the anion must be going to the left. All right, that loop has to be maintained there. It's a circle of life. There are different types of batteries out there. The nickel-cadmium battery is pretty interesting. It's layers. You can imagine there is a, zoom in on this one. There is a plastic layer. On top of the plastic layer is some sort of metal. And then on top of that is a light thin separator. And this is usually porous, like a piece of paper, if you will. And then on top of that is your other metal. And then it is all rolled up. And then there's tons of surface area in here as it's rolled up on top of itself. And the electrons can be exchanged through that piece of paper as they go. I mean, the anions get exchanged through the piece of paper as the electrons leave and come in one side and the other, which I think is pretty cool. Guys who figure that stuff out are brilliant. The old voltaic pile was just a series of metals sandwiched on top of each other with a separator in between. And then the dry cell battery kind of has a big salt bridgey stuff here. The zinc plate at the bottom slowly dissolves into it, and then we eventually have failure of the zinc, and you get your battery to corrode and leak. I think we've all opened up something and seen, dying batteries inside. It's because this piece of metal at the bottom slowly corrodes and leaks, which is pretty cool. All right, we'll talk more in the future.